AI has just achieved an amazing milestone. A couple of alpha models by Google DeepMind scored silver medal level performance in a globally recognized competition in advanced mathematics, IMO 2024. IMO stands for International Mathematical Olympiad, which is a contest that's been held annually for 65 years. It's definitely the oldest, the largest, and most prestigious competition there is for math students who practice very hard to be ready for the 6 exceptionally difficult problems that they will face in algebra, geometry, number theory, and combinatorics. Not surprisingly, these same difficult problems have become an enticing target against which to test the capabilities of advanced math and reasoning systems that are built using AI, trying to match themselves against the performance of the best and brightest students from around the world. Actually, the human side of this is quite interesting in itself. Scattered throughout history, there have always been a select few remarkable people who've been able to do math at another level far above the rest of us. One example is Srinivasa Ramanujan, the self-taught mathematician who shocked the world a century ago with his amazing ability to see remarkable patterns in numbers that no one else could see. The patterns often came to him in vivid dreams, resulting in very substantial contributions to pure math, including solutions to problems then considered unsolvable. The noted English mathematician G.H. Hardy at Cambridge University was the first person to recognize the extraordinary nature of Ramanujan's very unconventional work, including groundbreaking new theorems. In his notes, Hardy commented that Ramanujan's proofs included some that, as he wrote, defeated me completely. I had never seen anything in the least like them before. Another example is Volker Strassen. Literally for centuries, all mathematicians had accepted as gospel that standard matrix multiplication was pretty much the only option. But in 1969, Strassen shocked the world again by showing another way, which used one less scalar multiplication for multiplying 2 by 2 matrices. He was able to use 7 instead of 8, so that was more efficient. These are just 2 examples of very remarkable people. So the question is, can AI perform at that level, creating new theorems or solving problems thought to be impossible? Yes, it can. For example, 2 years ago, Google's AlphaTensor algorithm was able to improve upon Strassen's solution for the first time since it was discovered 50 years ago. Also, the traditional matrix multiplication method taught in school multiplies a 4 by 5 matrix by a 5 by 5 using 100 multiplications. But AlphaTensor discovered a way to do that same operation using just 76 multiplications, which is less than any mathematician had ever discovered. To do that, the model was trained using reinforcement learning, starting without any knowledge about existing matrix multiplication algorithms, gradually learning and improving over time, eventually rediscovering Strassen's formula, and then quickly surpassing anything that humans had ever done. And last year, DeepMind tackled the cap set problem, which is a problem that's stumped mathematicians for decades. The challenge is to find the largest possible set of points in a high-dimensional grid where no 3 points lie in a line. That problem cannot be solved by brute force computing because the number of possible methods exceeds the number of atoms in the universe. So that's a lot of methods to consider. By the way, that statement about atoms comes from Google. I myself have not personally counted the number of atoms in the universe or the number of methods and compared the two. But anyway, DeepMind was able to discover the largest cap set ever found and the largest increase in the size of cap sets in 20 years, as conceptually illustrated here. So that's the context. Now, let's talk about those problems at IMO 2024. This young fellow you see here is Haojia Shi from China. He was the top contestant this year with a perfect score, the only one to do that. Imagine a test so hard that only one person in the world can ace it. I'd say that's a hard test, my friend. So, Google deployed its alpha models to go after this. That's the same family of models, by the way, that previously learned how to master chess and Go. And here's how the scoring worked. 6 problems, 7 points possible per problem. That's 42 points, maximum possible. And here's the result for the alpha model. Both algebra problems were solved. The number theory problem was solved. The geometry problem was solved. Here's a look at that particular problem to give an idea. The contestants were asked to prove that the sum of angle KIL and angle XPY equals 180 degrees. In response, Alpha proposed to specify E, a point on the line BI, such that angle AEB equals 90 degrees. This new point gives purpose to the midpoint L of AB, creating many pairs of similar triangles, which were then used to prove the conclusion. All of which it did in 19 seconds. Unfortunately for Alpha, neither of the 2 combinatorics problems were solved. But for every problem that Alpha did solve, it got a perfect score. And one of the problems it solved was the hardest one in the competition, figured out by only 5 of more than 600 contestants. So, add it all up, 4 problems solved, times a perfect 7 on each one, that's 28 points, which ranked Alpha at the top end of the silver medal range. In fact, gold medal status started at 29 points. And we know that some of the students spent thousands of hours preparing for IMO. So, how were the alpha models trained? Turns out, AlphaProof trained for IMO by proving or disproving millions of problems. Unfair advantage. And AlphaGeometry 2 was trained from scratch on an order of magnitude more synthetic data than its predecessor, helping it to tackle much more challenging geometry problems than before. In fairness, the ability of AI to compete at this level does merit to be called a milestone. So, where does this lead us then? What are some applications that might benefit from this kind of AI capability? One might be fundamental physics. It's possible that this level of capability might now be ready to make meaningful contributions that develop new theoretical frameworks in areas like quantum mechanics or string theory, for example. Another might be materials science, accelerating the discovery of new materials that have special properties, like new superconductors or lightweight but very strong materials. Predicting this requires an understanding of very complex atomic and molecular interactions. Yet another might be financial modeling. Financial markets are complex systems that are influenced by numerous factors. Granted, today's existing neural networks can already analyze market data, identify patterns, and predict trends, but there's opportunity to improve, especially for things like derivatives and certain kinds of insurance products. There are other possible applications too. But one thing is for sure, if there are problems out there that have more solutions than all the atoms in the universe, then we'll be keeping these models busy for quite some time to come. Meanwhile, thanks for watching and see you next time.